Yeah, two files I have shared to you.
Yes, sir, received.
Yeah, you can have display of those files so that we can start.
So can I share this, sir?
Yes, yes, please.
Okay. Requested to mute your mic. Hello, Vishal.
Boleh, boleh.
Gopal Patil, sir. Patil, sir. Good morning, Manama.
Good morning, sir. Good morning.
Okay, can you start this session, sir?
Gopal sir, may I get YouTube link also?
Yes, sir. Yes, sir. Sure. I will share.
Please, yes, so that I can share it on my side, and then we can start.
Sure, sir. Sure. Okay, share to you, sir.
Gopal sir, just a query. This link says FDP on EV day 4.
Wait, sir. Wait.
Yeah, please confirm.
Sakit, sir.
Yes.
Day 5 is there. Means we have mentioned day 5. Please check once again. Because FDP on EV day 5 is showing right now.
What I click on, I get FDP on EV day 4. Yeah, Gopal sir, I got it.
Okay, sir, can we start the session now?
Yes, definitely.
Okay, sir, fine, thank you. Okay, so good morning, one and all. So this is day 5 and final session of the FDP on recent advances and challenges in electric vehicles. Before start of this session, let me introduce our today's speaker, Professor Satish Patil, sir. We all know that today's session topic is modeling and simulation of EV, that is electric vehicles. So, about this, sir has experience of over 19 years in the academic. Sir has guided more than 13 PG dissertations also. Sir has conducted more than 4 to 5 sessions on electric vehicle domain. In this, one funded project is also there in the field of transmission. Sir has expertise in MATLAB coding and simulation. He has completed his PG from IIT Madras and UG from Walchand College of Engineering, Sangli, Maharashtra. Sir has joined MIT ADT University in 2018 and immediately took up on vision of MIT ADT University, being New Age University. He, along with Professor Shashank sir, is instrumental in starting PG course in electric vehicles in academic year 2019 and 20, and UG course in electric vehicles in academic year 2021 and 20. Sir is also MIT ADT EV team, ADT team knowledge partner for Tata Motors and John Deere. Sir has trained more than 100 students and professionals in modeling and simulation of EV. So, welcome, sir. Welcome to this 5th and final day of FDP, National Level Faculty Development Program on recent advances and challenges in electric vehicles.
Yeah.
Now, you can start the session, sir. Over to you, sir.
Yes. Just allow me to share my screen.
Yes, sir. Yes.
Is this visible on your side?
Visible, sir.
I hope it is visible in presentation mode also.
Yes, sir. Yes, sir.
Yeah. So, good morning, one and all. Once again, I, Professor Satish Patil, belongs to MIT ADT University, and I am here today in front of you all on the cause of the FDP organized by KJ College of Engineering and Management Research on the topic recent advances and challenges in electric vehicles. Particularly in this FDP day 5 session, being the last session, of course, that is the need of the topic title also. Title goes modeling and simulation of electric vehicles. Before this, last 4 days, those all participants who are new to this field as well as little bit conversant with this field have gone through 4 different topics, right from Nibandhi sir, then Gopade sir, and on the third day Vani sir, and yesterday my colleague Professor Shashank. Yes, definitely we too, along with our colleague in the MIT ADT University, are working hard on this electric vehicle domain, and that's the fruitfulness where we are knowledge partner of Tata Motors as well as John Deere. Okay, so thanks to the Gopal sir for introducing me, and now this is a position to start the session. I hope all are ready with their laptops and mobile. So I'll take forward particularly this modeling and simulation of EV. Today's session will talk about three phases, and those three phases goes like this. The first one, which talks about MS, that is modeling and simulation, and MBD, that is model-based design. Second phase will take that modeling and simulation to EVs, EV applications, of course, and then we'll have a case study of modeling and simulation of course, EV. So let us start with the first module or first phase, modeling and simulation. Okay, just to going into the first phase of this session, I would like to put what would be the prerequisite and objective. Okay, the thing is, as I said, the last session, as per the need of title of the topic, modeling and simulation. This of course need a little bit prerequisite because we cannot jump directly to the modeling and simulation of EVs because the prerequisite for this particular topic goes with some of the MBSE, model-based system engineering knowledge, some of the performance parameters and their dependencies, of course, in the automobile domain, and then electric vehicle powertrains, different configurations. And I hope earlier few sessions have touched upon at least different configurations of powertrains and different components of powertrains like batteries, motors, and power controllers. Okay, and also the first session which was being conducted by Sanjay Divandesar, of course, he is connected to us also, and we get a lot of guidance from Sanjay Divandesar also. Okay, with this particular prerequisite, we can go with the objective for today's session that we'll get to know a kind of virtual or combination of physical and virtual tool or a technology which allows us to study the EV domain, and then we look after some of the modeling of powertrain components, how it goes, what are the types of modeling of the components goes. Then with the case study, we can focus upon simulation of a particular powertrain which we are talking about, and then some of the discussions on interpretation of results and how do we take care of those results, and then improvisation based on that. Okay. Well, with this objective, I'll move forward. Just I'll touch upon because you have gone through extensively. I listened the session of Vani sir also. He has exhaustively gone through how EVs are developed over the century, and he has exhaustively talked about all phases of EV development, year-wise also and technology-wise also. I just put two news in front of you as in development of EVs over the century. Okay, so just there was one news in the French newspaper in the 1893, and what it said: human inventiveness has still not found a mechanical process to replace horses as a propulsion of vehicles. So we are talking about the era where horses were being used for the propulsion. Okay, that's 1893. So you can check it out, the news, which is followed by a horseless carriages race in the following July. Okay, so the new news and then race organization, and then if you look back some of the facts on that race, yes, there were 102 entrants, okay, for the propulsion of vehicle without horses. But then it was a combination of steam, petrol, electricity, compressed air, hydraulics. Only 21 qualified out of them for the 126-kilometer race. And surprisingly, yeah, the clear winner was ice. Now we are talking much about replacing ice with the electric vehicles, right? But then we need to know that electric vehicles or the electric power has been used as the propulsion much before IC engines. But then developments over the century provided that IC engines are a little better than electric engines, but then we go for now because of some or other reason we are turning it from ICE to EV. Okay. Now you all already aware of the reasons and all, so I will not talk about that. With this, one of the incident in the 1893 and followed July race, I'll take you to the current era where most of you have been witnessed. In 2017, there was a news in the Economist about what? The clear winner was ice before the century, but then now we are talking about death of ice, internal combustion engine. Well, this was the news, but definitely this is the era where 2017 and thereafter and even before that, whole automobile industry turning to the electric vehicles. But then the question is not about ICE, whether it is on deathbed or it will still continue. The question is, over the century, the development was standstill for electric vehicles. But then, is it time come for electric vehicles, battery electric vehicles, having future ahead, maybe 30 to 50 years ahead of now? That is the question. So we are here, all of us, eagerly wanting to know about this particular domain and how we can progress in that. So this is what question in all of us mind. Do pure battery electric vehicles really have a future? Yes, of course. The answer lies in what efforts we are putting in that direction. Okay? So as you are registered for this particular FDP and you are attending all these sessions, of course, all of you are also after this question. Am I right? I hope we are in line. Well, I'll move forward. I'll just take one kind of participants poll. Just I'll request all participants, please go through this QR code and this Google form. I'll put it on the chat also. If you are on mobile, you can scan the code. If you are on laptop, you can access this Google form through chat box. Is it available in your chat box? Hello?
Yes, sir.
Yeah, and those who are having mobiles, they can scan QR code and go with a short survey. There are only two questions. So we are finding the answer to the question, do we have electric vehicles in recent years, in upcoming years, do we have really a future? Will it be playing a role in the automobile industry alongside ICE, if not alone? If alone, that is well and good. So, are you all accessing this QR code and Google form? If anybody could answer. Is it accessible, first of all? take 1 minute. Yeah, we got 12 responses. You can see. I hope we should get more than 12 so that we can get what exactly we are having. The group with which I am discussing, I would like to know about them, about how they are interested, how they are aiming, what their objective to attend this FDP, as well as at what level of learning they are. I hope there are many more participants than this. What I see in the Google Meet link 101 and on YouTube, there are many more, right, with us. So once again, I'll share QR code with you so that you go through these two questions. What it says, it gives us idea about your learning stage and also idea about, particularly for this topic, modeling and simulation, where do you stand? Yes, please. We are getting more than 20 now. What about others? Are they able to access the QR code and link? It will hardly take less than 1 minute. If you are taking, you can access through laptop, through the chat box, Google Form link. You can access through mobile with this QR code.
माझं जॉब कधी
Yes.
करताय कधी करताय मग कॉल
Yes. Anybody? Anyone want to say something? Someone has his or her mic on.
Sir, hello. Yes, Bob, sir. Are you want to say something?
Yeah.
Bob, sir. Hello. Sir, how can I access this form?
Yeah, it is. The link is in chat box, Google, and if you are having this screen on in front of you, you can scan this QR code. Gopal sir, if you could get this link on the WhatsApp group also, that will be also fine.
Yes, sir. I will share. I will share it to the WhatsApp group.
The link is in chat box. You just please share it on the WhatsApp group so that everybody can go through it.
Share it in WhatsApp group also, sir.
Yeah, thank you, Gopal sir. I could get responses almost 30. Come on, I have many more participants on the Google Meet, right? I am able to see 101.
Dear participants, please submit your responses. So that sir will get a clear idea about today's session.
Yeah, we can orient our session accordingly because it goes.
Yes, sir, yes, definitely.
I hope this Google form pie chart is visible to all of you.
Yes, sir.
Yeah, so everyone can take a guess that how exactly where we stand. How about all participants? How they are interested to know about with what objective they will be attending this FDP or rather this modeling and simulation session. Yeah, good to say that crossed 50. I'm expecting within next 2 to 3 minutes it should reach 100 or even more than that. Gopal sir, if I'm not wrong, we have many more participants, right? Registrations?
Yes, sir. Near about 570 participants are there.
That's what. Everybody is eager to know about EV domain, but then, yeah, hats off to their efforts. They want to know about EV domain, they want to attend, they want to learn from different sources. Yes, definitely, that's a great sign. So the answer to the question of electric, do we have future for electric vehicles? Yes, it is in right direction there. Even in this pie chart, you can see there are many of the participants which are new to the simulation domain, but then, yes, of course, they have got opportunity to go ahead with this. Just understand one thing. We got more than 500 participants here for this FDP, and all of them are eager to learn about electric vehicle domain. And there are very less sources available in the market about electric vehicle domain. Okay, so definitely it needs a little more hard efforts to go ahead with this particular direction. And everyone do not get a chance to interact with research organizations or apex bodies like ARAI, SAE. Many educational institutes nowadays are starting with such kind of courses. Even all universities are getting ahead with minor courses in electric vehicle domain. But then if you look back this pie chart on the top, you see we have more working professionals which are working after their post graduation, and they are rather more interested in this modeling and simulation session. Okay, now to have this kind of crowd, and they will be looking for many resources around to learn this technology. Definitely, it has got to be different platforms to learn ahead. Yes. So I'll take full stop here for this particular survey, and we'll continue with our discussion. Okay. So this is what scenario just to go ahead with. We have almost 30% of the crowd who have given responses who are new to the simulation domain. 24% are attending session out of personal interest. Yes, that is required for the field to go ahead. And 39%, almost 40% of the crowd is upgrading their simulation knowledge and in the for the ongoing and upcoming projects. And there are very few who are regular user of simulation tools. Yeah, even then, having said that, simulation tools might be used for different purpose. Different simulation tools we may use. Okay, so we'll have a full stop here for this. It crossed 90. The link is available for your use. You can complete it later on also. Okay, so I'll move for the topic. Yeah, these were the questions, and we saw how the responses were from all of you. So you also know how your friends or colleagues who are attending sessions are standing at what point, and then how they are expecting out of this session. Okay, so I'll go ahead, going through development over century and having a question in mind. Also, going through this form, and we'll understand where we stand as per our learning stage, as well as per our simulation, modeling and simulation knowledge, or you can say the where we want to take this modeling and simulation ahead. Okay. Well, thank you. We'll start our session. As promised, the first phase, we'll discuss about modeling and simulation and model-based design, wherein making a model was not new to us, or rather, nowadays it is not at all new because we have been modeling many things, of course, with the different objectives. The first objective for model, which we are talking about modeling and simulation, that is nothing but it's an abstraction of simplification, isn't it? Now, if I go ahead with what model gives and how it provides the insights to the behavior of the complex systems, and then how it gives idea about in what direction we could improvise upon the particular product. Okay, and then when we have different components put together, that forms a system, right? And then we get model of full system, and then if we want to perform that system in a proper manner, in an optimized manner, we go with simulation, isn't it? So modeling and simulation, we model some of the things, we simulate over a system or over component level also, individual component level also, and we know that some of the models on the component level perform better, but on the system level, if they put into, they may not perform at the optimized level as per the system demands. Okay, so we have modeling and simulation, that's the process. Now, at this particular era, we are talking about the development in EVs, and we are talking about modeling and simulation of EVs. And one of the major role played, because we are talking about modeling and simulation, that's the computation. Okay, so we have computational techniques, or we have infrastructure to go with computation has been developed already at this stage. Maybe this was one of the reasons before 100 years the EVs did not took up, or EVs do not overperform ICE, isn't it? But then, if you look back, how advances in the computational power or scientific modeling happening, this is a table. It may not be clearly visible, but at the end, I'll go through some of the books so that you can check back for the particular technology modeling and simulation, few books you can refer. See, this table gives us idea about 1950 to 2014, how development of computational power and scientific modeling happens. Okay, so it was all started with theoretical chemistry, and then it goes to the aeronautics and structures, and then software and algorithms were started to build. Okay, so that's where we are using uh, softwares, more and more virtual platforms for modeling and simulation, and that's the advantage of today's era. And as we are fond of doing most of the things virtual nowadays, this is a right platform to get ahead with, and this will fetch many new entrants for this particular technology and then development in this technology. Okay, of course there is development after 2014 also, but then we are almost aware of what the development is all about. Now see, this slide gives you idea about what exactly the modeling was. Earlier it was physical prototypes, we call it as mules, but nowadays we are going for virtual prototypes, virtual modeling. Okay, so you can check it out. The 2005 Toyota Avalon did not get any physical model at that time in 2005. So all was done using computer modeling to design and test the car. So that was all virtual. You can see there were the era where physical modeling, physical prototypes were made and then tested in the automobile industries also. Other than automobile industries also, of course, there were modeling. Of course, for an example, you can take dams were constructed as good as a real dam, and that was the model. Almost a kind of 1:2 or 1:3 scale model physically. Likewise, it was in the automobile industry also. Might be you have gone through in your earlier learnings that physical prototypes were prepared and then scaled down models and then they were tested and then improvisation was happening. But here we have around 2005 without physical prototypes and all, we were able to get computer modeling and design and test the car, particularly in the automobile industry. Yes, that was the case. Just this slide gives you about idea about what exactly modeling is, but then yeah, this is what the very fundamental or book definition for you. Okay. Of course, we are interested in when we say model, that should represent physical phenomena of that component or of that system. Okay. We'll go ahead with mathematical models turned into virtual models. There are steps involved in the modeling, how best the modeling can be done for particular components or systems. We go with some of the problem analyzing, then we define objectives, then we create a conceptual model, then going for simplified assumptions. Of course, this is the major step where we go ahead with. Whenever we start modeling, we go with simplified assumptions. Then thereon we can improvise upon some complexity level. So after all, we need assumptions to start with. Then going with different variables, different relationships, then implementing it in the computer model, interpret results, and then go back again with the variables, validate that model, and then make use it for different other purposes like post processing, then analyzing and reporting, and then drawing some of the conclusions how best that particular system performs. Okay, so we go back here and there with earlier steps and then improvise upon. This is what routine modeling steps we do follow for improvised models. Okay, but this is what been happening in earlier years. So we need not to think about this particularly because much more simplified or much more improvised versions of models are available right now. You can add here and there with your objective. Yes, definitely we can do that. Well, going to the simulation, it's a process where the model is get into simulation where across the time it will be run and it will get us to the performance parameters which will be checked upon for validating that system, for validating that configuration, okay, at system level, how the performance goes. So we do get some of the benefits like deliver innovations faster while maintaining safety and reliability. And of course, we all know that being vehicle simulation, which is simple or complicated depending on the requirements and objective, but cost-wise, if you say that is cost-effective because we are all doing it on a virtual platform. Virtually, we are doing it, and we are guessing out how exactly the the system is going to perform. But then we do get with the some of the trade-offs in between. Particularly, this is talking about automobile industry, energy efficiency, and acceleration performance. We'll talk about that in later on. So this is what simulation gives us idea about. Now I'll move forward for model-based design. So this particular slide in front of you gives idea about what we were doing in the traditional or conventional design process. Okay, what were their drawbacks? And on the right hand side, you see on the screen more greener to look, and that is what we say, right? Model-based design. So we have some positive points, green points on the model-based design compared to the red points on the conventional design process. The major things you would like to know about model-based design is this arrows, these arrows. See, we were having forward arrows in the traditional design process, but we were short of reverse direction arrows in the traditional design process. I mean, don't take it word to word. Reverse direction arrows means the process which we were able to follow. We will go back to the earlier process. We will accommodate changes in that. We will accommodate changes in the earlier steps, and then we could proceed further. So that is the beauty of model-based design process. And if this process is happening virtually, that is icing on the cake, isn't it? So we are learning about the model-based design and how it can be done with the virtually. So we are using model-based design, which enables, of course, front loading of EV development, whatever at the front EV development happening through systematic use of data and different models. Okay. Of course, there are different tools to go ahead with. We will not stick to any tool, but as a case study, as one of the case study, we'll go ahead with one of the two. Well, having said with the comparison of model-based design process and traditional design process, if you check back with what exactly model-based design gives in a nutshell. So these are the 8 core concepts on which model-based design process emphasizes. So executable specifications, system-level simulation, what-if analysis, model elaboration, virtual prototyping, continuous testing and verification at different stages, component level as well as system level, automation, and then and as a aim, as a the true benefit or fruits of this model-based design process is knowledge capture and management. Okay, so with these core steps and advantages over the traditional design process, we go with virtual model-based design process with the tools available. This is what workflow of model-based design, particularly for EV simulation, and that's what we followed with automobile industry many days before now. Only the thing is, we are learning to adopt it for EV development. So this is the slide with one of our connects, that is MathWorks. We are in close connect with MathWorks team also to go ahead with uh, how modeling and simulation will be utilized for EV development. So this is what we structure we have. Start with system requirements, then system architecture, system design, component design at the individual level, then software design, and then embedded code generation. And then these all code generation, software design will be tested, software in the loop, hardware in the loop with two different ways, then taking out the calibration, and then of course validation. Are we really in tune with the system requirements with which we started? And then the product will come out in the market. So there are a few companies which are working on this particular, and there are many startups which are not working on this. So it is hard to get your footprints in the market without going ahead with model-based design workflow, because if something goes wrong on the ground level, then improving it and all that goes very tedious process, isn't it? So if at all you adopt this kind of approach, this kind of model-based design workflow on the virtual domain, if it is there, then that is well and good. You will find very less failures on the road. So we hear about many companies putting their EVs on the road, and then they are taking back, they are taking for the development, they are taking for the upgrading the softwares and all. Yeah, that is bound to happen because we are in development stage, and we need to cope up with that. As a customer, of course, we do not want that, but then in the development stage, this is bound to happen. Okay? Yeah. With this, we can go with second phase of the session. I hope we are at good pace. Gopal sir.
Hello, sir.
I hope we are at good pace.
Yes, sir.
Yeah. So entering into the second phase of the session. Now, let us understand how exactly this model-based design process, or particularly modeling and simulation, will be applied to MSCV. This is the topic of discussion in this particular FDP. Check it out, how exactly modeling and simulation will benefit in EV. Being at the development stage, we are worried about component selection, which components to be selected for the powertrain configuration, what exactly the requirements of the electrification of powertrain are. Now, being a day 5, you all are aware with what different components we need in the powertrain of electric vehicles. Then definitely these questions would have come in your mind. A few of the session speakers might have touched upon this in their earlier discussions. Like if I am worried about what kind of battery I will be choosing, there are different batteries. Shashank sir discussed yesterday also, right? But then, how exactly for my requirement of the powertrain, how am I going to select which battery? So component selection and of what size, component sizing, and then at the end, how all these components, motors, batteries, controllers, if they are all there put together, how the vehicle, a full system will perform. And if at all I am going for optimization in that particular powertrain, how am I able to get optimization, optimized performance of that powertrain? Okay, of course, modeling and simulation focused on the powertrain, but then there are many more components which are taking part in the development also. And this modeling and simulation of EV powertrain is one of them. Particularly, how do we select components to work together? How does the vehicle perform? That is the question which we may face in. With selected components, let us say we have selected the components to go ahead with batteries, motors, controllers. Then what would be the fuel economy or range which customers from their point of view, their use point of view, they will be looking for how it can be achieved, how it can be, this demand of the customers can be fulfilled as a OEM or as a vehicle manufacturer. Okay. That is need. In other way, we can say this all need arises because of the challenges which we are facing. The challenges in EV, architectural or topology selection, and then selection of component, complexity, modeling. Because when we say modeling, that could be done at different levels with different assumptions level. Okay. And then optimizing the performance, implementing real-time control algorithms, because we do have controlling algorithms, but are they optimizing the performance in the real-time basis? Okay, or is it predefined control algorithms? So that way, we do have challenges, and this modeling and simulation with these needs maybe giving us answer to the some of the questions, of course. Well, to be specific, if I want to put a kind of problem statement in front of us to go ahead with for the EV modeling and simulation, this could be like the minimizing few of the components in the powertrain performance, at the same time maximizing some of the components in the powertrain performance. So, for example, you can see all of us would go for having energy consumptions per kilometer very on lesser side, isn't it? So that whatever energy capacity battery we choose, with that we should get more and more range. Okay. So if at all I'm considering for energy consumption per kilometer on lower side, I would get range per energy capacity that on the higher side. So there are few parameters with which we can minimize with few parameters with which we can maximize upon. Now we know as far as vehicle speed is concerned, we want to be at the maximize as customer demands, but there is a limit for the EVs how max vehicle speed can go ahead with. Okay, because that's all one of the defining parameter to go to get more and more range. So there is a dependency in between variables, and then because of which we call this as, instead of minimizing few parameters and maximizing few parameters, we call it as both these put together as optimization, isn't it? That is what optimization has been doing since many decades. And there are many tools available. We can go ahead with different controlling strategies, different optimizing strategies for particular powertrain also. Then all these variables, of course, not free to work on their own. They are subject to some of the conditions, isn't it? So we have constraints to work with, maybe in the form of limits to the power or battery, a velocity within the window of drive cycle velocity. Okay, and also when I say actual limits of battery, it goes with SOCs, isn't it? I hope everybody is aware of what SOC is, because yesterday only we talked about batteries in detail. Am I right? Can anyone? What is SOC? Hello?
State of charge.
State of charge? Anyone else? Anybody else? Well, I hope you are aware of what SOC is, and we do have limits, lower limit and higher limit, and we would be happy to operate between these two limits as far as battery performance is concerned, and then it will give us optimized performance of the electric vehicle. So, with this kind of problem statement in front of us, a different vehicle manufacturers will be having different objective in front of them with different restrictions in front of them. Okay, as per the segment of the vehicles, as per their capacity in the market, they go with, isn't it? Now, if at all this is the problem statement, if you see exactly what modeling at the component level is, because whenever we say modeling of the components, we do go ahead with mathematical model and that way expressed with the software tools, isn't it? So equations and then working on those equations with some of the assumptions coming along with that, isn't it? So this gives you idea about how different types of component modeling could be accommodated in the simulation process or modeling process. Okay. It goes with first principles models, data driven model, and behavioral model. Here, we can have individually as well as we can have a combination of all these in our particular simulation. We're not worried about how a combination we are doing because these types, first principles, data driven, and behavioral, gives their own advantages and disadvantages. Okay, so we could have combination as per best suiting to the approach which we are dealing with in this simulation. If I go with one by one, the first principles model, it really talks about equations, physical equations. Now you check it out on your screen. I have taken a case of motor operation modes, and if you have motor operation modes, of course, we are aware of what motor gives advantages over ICE. We do get propulsion mode as it is required as a fundamental requirement. Additional advantage the motor gives is regenerating mode. Okay. Along with that, we also need a kind of third mode, that is spinning mode. So you check it out on this different modes. We have equations to deal with. We have many equations to deal with where we also have the parameters to deal with. For example, efficiency of the motor. For example, efficiency of the motor, that is altogether it is considered on this slide as the combination for motor, inverter, and controller. So that is the efficiency of motor we have considered in this particular equations. So you check it out how torque demands as far as vehicle goes and how the losses in the component and how dynamics of the motor works. Okay. Based on that, what would be the torque the motor would be giving? Okay. And there is a constraint. What could be the maximum torque motor could deliver? Okay. Which is of course a function of angular velocity of the motor, the rotor of the motor. Then these all equations needs to be modeled carefully because there are certain constraints, there are certain dependencies. For example, lost torque in the motor having different components. Okay, it all goes with the time duration, it all goes with angular velocity. Okay, then required electrical power with that, with the consideration of torque provided. So we do get the power, and accordingly we define a kind of the parameters motor would be working on in particular propulsion mode. The same thing if you check it out with regeneration mode, it is little different, right? We get torque demand and we are generating torque on the motor which should be fed back to the battery, which should be preserved or accumulated in the battery. Okay, so whatever dynamics the motor gives, accordingly we should have the modeling. Now, having said that, if you do get a kind of propulsion mode and regenerative mode with these physical equations, yes, this could be modeled with different tools where the model of the motor would be working on this particular equations, physical equations. So that's what we call it as the first principles model, because they are actually working as good as their physics course. Okay. Of course, this should be a more accurate based on the kind of assumptions we are making. I am saying more accurate compared to the data-driven model or behavioral model. Compared, if I talk about with reference to assumptions, depending on a level of modeling, the accuracy goes. So we have equation-based modeling, which will be giving us more correct results. But then, if this is the scenario, we know on the computational side, this consumes little more time, isn't it? And this is a difficult process because not everyone is compatible with modeling with the equations. Not everyone is compatible with mathematics, rather applied mathematics, isn't it? So we know mathematics as an engineer, but applied mathematics that requires little more skills, isn't it? So this first principle models, although giving some accurate results, but then on the other side, we check upon how assumptions we are making and then how computational infrastructure are available with us, and then how fast we can go ahead with the simulation process or this development process. Okay, so this one where we have spinning mode, so there is no torque delivery or torque generation happening. So whatever we get in the motor, that is a kind of loss only. And the spinning mode, you can correlate this particular mode of the motor with the neutral position of the IC engines, what we experience already. Okay. Yeah, so if anybody is interested going into the details of this first principle models of these physical equations, I have quoted a reference here, the book with which we can go ahead with understanding a kind of equation-based performance of the component level. And of course, this book also gives at the system level also, which we discussed in line. Now, having understood about this particular type of modeling, first principle models, and how we can get into physical equations, this is the second case where data-driven modeling. Okay. Now you see, we have a dependency. For example, we talked about motor torque dependent on motor speed. Okay. But then we have efficiency of the motor altogether dependent on both parameters, torque and speed. Then this is happening with the efficiency. Okay, where I do have these efficiencies, these maps could be utilized in the modeling as a steady state map, where we have data already available with us for different types of motors as it is given in the display on the screen, and you will make use of this available data for using it in the system level modeling or component level modeling, so that we are not bothered about how physical equations are working and how they are delivering for the simulation, but then we directly quickly jump upon what could be the efficiency motor is working on, having the torque, having the speed. Okay, so you can see there are different patterns, different efficiency for the different types of motors. Okay, so this could be checked out with the different simulation tools with the kind of lookup table, either in the form of table or directly in the form of data available in the form of map. So, of course, this is a kind of static because we are using ready data, but then we can add dynamics with it with the transfer functions, a little complicated one, but yes, we can do that and we can make use of data-driven models. Now, we have this particular compared to the first principle model. It will take little less time because we are using pre-ready data, predefined data, but then accuracy, considering dynamics, goes on lower side. Going to the third type, this has been said as behavioral model. Again, little simpler than earlier two first principle model and data-driven model. But if you check it out, a battery chemistry how complicated it is. You might have gone through yesterday's session of Professor Shashank. He has discussed in detail how chemistry goes, isn't it? But then, exactly model that chemistry and those physical equations, if I go upon first principles models or data driven from those batteries, then it becomes difficult. So it is a little bit wise to go with behavioral model, how exactly the battery behaves or how the voltage gets out as a parameter for the battery. Then we could devise a equivalent circuit of the battery and we could get it exactly as good as similar response as the actual battery gives us. So we are preparing equivalent model which produces similar dynamic response. So this is one of the uh, slide or the image taken from the MathWorks, which gives you idea about simulated performance and experimental performance. If a battery is performing experimentally, this delivers voltage in this similar pattern, and simulation is also following same pattern, almost same pattern with the actual battery. Okay, so we do have kind of model, kind of equivalent circuit battery which will be used for our simulation. So this gives us added benefit that instead of going to the complex chemistry of the battery, we can use the equivalent circuit and we can simulate the performance of the battery as good as actual battery. Okay, and this kind of circuits can be used, as we know we are working it on cell level, module level and pack level. Yes, these all circuits can be used at different levels also. If you look back in the equivalent circuit battery, we have a capacitance and resistors, right? So combination of that which gives us dynamics of the battery and which is performing, which is simulating as good as actual battery, and that is additional benefit on the computational side. Okay, so with these different types, I will jump upon a kind of a system level modeling and analysis. Okay, see, I have taken a case of two-wheel drive electric powertrain, the pure electric, which is working or propelling on electric motor alone, not IC engine or any other power source. See, this is the schematic. Now we all know. Once we say vehicle, we all know we have a kind of power generation unit, then gearboxes, transmission units, with the kind of transmission box, differential box, and then we are delivering it to the wheel. So what vehicle demands at the wheel is being provided by power plant, isn't it? So in this case, it is an electric motor. Now, if at all we are interested in simulating or modeling this with the equations, there is a kind of text, but eventually this PPT I will share with you through the coordinators. The PDF will be shared, of course. We are interested in kind of learning how exactly equation goes. See, this is one of the example. Uh, I hope, if I'm not wrong, Gopade sir in the second days talked about motors. Am I right, Gopal sir?
Yes, sir. Yes.
Yeah. So this might be one of the equation you might have gone through in that session where particularly the electric motor operates in two phases. There is a base speed, we can call it as a critical speed. The motor works in two phases, less than base speed and more than base speed up to its maximum limit. So there are two phases with which this torque generation in the motor happens. Because these two phases are called as, here we say that constant torque phase, and in this phase we say that constant power phase. Okay, so the torque generation happens in the constant power phase with respect to combination of angular velocity of the rotor and the maximum power generation capacity of that motor. So in the first phase, at whatever speed up to critical speed, it is delivering constant torque. At the second phase, it is delivering a variable torque with respect to constant power, max power, or rated power generation capacity of that motor. So these two things can be accommodated also in the modeling and simulation. Like we do have this kind of equation, final equation at the powertrain level, where this equation gives us idea about the performance of the motor along with the transmission. This Fr is resistance forces. So whatever torque generated by the motor needs to overcome resistances by the vehicle, and then we get a kind of propulsion to the vehicle, isn't it? So of course there comes the mass of the vehicle, dynamic mass of the vehicles, because there are many rotating components in the powertrain which we need to take care of. So this equation B is as good as acting as a dynamic equation for the electric vehicle. Okay. So if at all we apply the two phases of motor to this longitudinal dynamic equation of the system vehicle, we have these two phases. Okay, this U represents the vehicle velocity. Okay, maximum speed can be found solving the equation U max. So we do get two phases for the vehicle also. See, this is the case where the scenario goes with different phases of the motor. Because we are talking about pure electric vehicle, we need to cope up with two different phases. Now we have certain other parameters to look after. So maximum gradability, how we can get ahead with the equations. These are all derivations which you can find it with the reference book which was given in the earlier slide. Along with that gradability, we can take upon the acceleration time, because these are the few parameters which are interested as a performance level parameters at the end, as a system level parameters, because everybody wants acceleration time to be on lower side. Of course, motors are more capable of giving acceleration time on the lesser side compared with the IC engines. So we know performance of the electric motor, but then how exactly it combines together with the IC engine and then vehicle system. Now, this is the second case where I'm talking about hybrid electric vehicles. Now, hybridization can be of different energy sources. Okay, we may talk about motors and ICE combined together. We may talk about different energy sources combined together. For example, batteries and capacitors. Okay, that goes. This particular equation gives you idea about how the motor and engine terms coming together and motor terms come together, both overcome the resistances of the vehicle, and then gives the propulsion torque required, the demand torque required to the vehicle. With this equation, okay, where dynamic mass, which I was talking about, can be calculated with this equation, but then we also have a kind of approximation. We take 5 to 10% of the total mass of the vehicle as additional dynamic mass. So MD can be directly taken this particular vehicle mass plus 5% of vehicle mass as a replacement of these all terms. Okay. So there are different ways to do. If at all we are interested in calculating actual, yes, because this dynamics depends on many parameters, all efficiencies, transmission gear ratios, and all those things. Okay, so efficiency, then this beta represents gearbox transmission. So this is what scenario we are talking about for hybrid vehicle. We do have engine with us, electric motor with us, and then we have a coupling torque coupler in between, which goes to the wheels through differential. Okay, so if at all put together all parameters for the hybrid electric vehicle. These terms comes in picture with dynamic mass. So efficiencies of the engine gearbox, motor gearbox, torque coupler engine input and torque coupler motor output. We do get gear ratios of engine gearbox, motor gearbox playing a role in that. Okay. So with this particular equation of J, we can find out how the electric vehicle powertrain will perform in the hybrid mode. Okay. And there are control strategies to go ahead with. So the controller part also plays important role, where the torque coupler will depend the performance, take the sharing from the engine side and sharing from the motor side. And different modes, of course, we have ICE only mode, electric motor only mode, or combination of these two, ICE heavy mode, motor heavy mode. Okay. Then regeneration mode. So all these things can be taken care by the simulations with the control algorithms. Now, having said with these all equations, of course, going ahead updated for the acceleration time and then variability, all those things. What exactly system level simulation demands or how it goes in a nutshell? So see, earlier to this we saw about how these all equations we could accommodate in this modeling of the subsystems. Okay, and this slide will give you idea about for HV powertrain, for EV powertrain. If at all we are modeling with different systems, storage systems, electric motor or ICE in combination or alone, and then power control components, then transmission, all put together we get a system, right? So power configuration, depending on the architecture or configuration, we do get a kind of availability of energy storage systems, different types, and a combination of power plants, motor or IC. Here, the systems will be checked back for this simulation for their performance depending on the drive cycle. So this also gives us idea about how different drive cycles could be utilized, different drive scenarios could be utilized. As far as Indian context concerned, we are using modified India drive cycle, not full, but in partial for electric vehicle developments. But there are other countries which are using many more drive cycles. Okay, and then based on these drive cycles, how the system which we are interested in is performing. So once simulation is complete, we are getting with vehicle parameters, the performance. If we interpret these parameters, we will be in a position to update or alter the parameters, improvise the parameters, system improvisation decisions. We can take it out where to areas to improvise and what to improvise, how to improvise. Okay, then we go back to the simulation again. The system will be updated accordingly, and for the particular drive scenario, we can simulate it again and we can validate it. So this system goes in the iteration mode, and if at all we are doing it on a virtual platform, this provides advantages to us. Okay. So this is what full scenario we have as far as modeling and simulation is concerned. We do go for modeling of different components put together, modeling of system, and then all this work together as in simulation. Okay, and the performance will be checked across different drive cycles. Okay, so segment wise, different drive cycles we may get because passenger car vehicles cannot be checked for same drive cycles where the low commercial vehicles will be checked. Altogether, performance requirement is different, so driving scenario pattern is also different. Okay, so that's how we can make changes in the driving cycles, and accordingly we can check out for the simulation. Going ahead, having said that, the details of modeling and simulation, what benefits we could get on the virtual platform for the modeling and simulation. So we are almost at the end of second phase. We are talking about key benefits. So of course it goes with reduction in prototyping and testing efforts, design alternatives evaluated in very lesser times than what we were doing it in the physical mode. Okay, not in months or years, it comes down to the almost weeks. So development can happen in the number of weeks instead of counting it in the months and years. It also increases ease of implementing complex algorithms because we are talking about real-time algorithms, we are talking about dynamic algorithms, situation-based algorithms. So this is what the expected nowadays. It is happening in many few vehicles, not many. But then how we can accommodate in the mass vehicles, the different segment vehicles. So we could have accelerated testing, supervised control algorithms, which could reduce the time almost by 50%. Then increase the scope or features of algorithms. We can expand our horizon where algorithms could take care of many more modes or working scenarios in different environments. Okay. Then field issues rapidly will be resolved because as we know, as we hear about many OEMs are facing different challenges when they put their vehicle on the road. On the road, they come across some of the issues and they will be resolved. So those issues can be resolved very early because customer is demanding that to be done at very faster rate, isn't it? So turnaround time for the dealing with issues, filling all these correcting bugs is reduced or dropped by 50% of the time because of the increased reliability and documentation of the complicated algorithms. So these are all key benefits which we may get if at all we are putting up modeling and simulation on a serious note. Of course, economically, all OEMs will get benefit from adopting this technology, but infrastructure-wise, initial level, we need to having spent or emphasize on this modeling and simulation. Okay. This slide will give you idea. The modeling and simulation we talk about the performance of the parameter of the vehicles, but we majorly say that most of the times that predicting the range of the vehicle, right? Now, this is not only the use of modeling and simulation. There are different other uses because the database which we get with the help of simulations at different point of interest, with which we can do many more tasks. For example, we talked about algorithm development. You see, we are getting data about acceleration effort at the motor phase, at battery phase. Okay, all this data we have it almost at the 1 second step or even less than that. Okay, the time step almost 1 second or less than that. So you can imagine a data at every second, how it could be useful for deciding, for taking some of the major decisions for putting up algorithms. Okay, and that's where we have the advantages simulations are. Okay, nowadays data analysis is taking a pace, and there is a term coming out in market. You all might have heard because many of you are working professionals with post graduation. Software defined vehicles. Have you heard of software defined vehicles? Hello? Have you heard of software defined vehicles? That's the next era which we will be talking about. some of you might be knowing software-defined vehicles. So you just Google out how software-defined vehicles are going through. I suppose in coming future we do have a conference of SE in the Bengaluru about this software-defined vehicles. Okay, you just Google out about that. The base of that all is data analysis and the data created by all these simulations. Okay, so we all using this data for betterment, for the performance betterment as well as for the totally jump in the technologically. Okay, now we'll go ahead with a third phase of our simulation. I hope you do not have any queries about first and second phase, where we discussed modeling simulation, model-based design, and then we discussed on how this modeling simulation of EVs can do occur. Okay. Shall we move on to the third phase? A case study. Hello, are you all with me? It could take 15 to 20 minutes more for the case study. Hello.
Yes, sir. Yes.
I hope I'm audible and you are all with me.
Yes, sir.
Shall we go ahead with the case study? Yeah, I'll jump to the case study. I'll come out of this presentation mode and then I will share my screen with the MATLAB simulator. Okay. Having said that, of course, you take it as a disclaimer that we're not talking about any one simulating tool, but a case study. For a case study, you will be going with a MATLAB Simulink. Okay, will more of focus our discussion on technology based rather than tool based. Okay, you see. Okay, is my MATLAB window visible to you? Hello.
Yes, sir. Yes, sir.
Information?
Yes, sir.
Is it visible my MATLAB window?
Yes, sir.
Yeah. Okay. Great. I'll just open up Simulink. If you are all aware, the MATLAB and Simulink, this is the shortcut to going to the Simulink. I have an open file with me here. You can have a look at this, the model at the vehicle level, which has got different components, different control tools, the vehicle body, entire system. There is an input to this model as a drive cycle. Okay. Particularly, I don't go into the details of how exactly MATLAB and Simulink would be utilized for simulation, but then I will focus upon how component wise and how the system level modeling can be done. So this part gives us as an input to the system. This will drive the system. It will take inputs from the drive cycle and it will feed it to the controller so that this motor would work, this motor and controller would work accordingly, and then it should fade through transmission to the vehicle. So this gives us idea about a kind of vehicle we have along with the braking system. So few of the things are considered here, few may not be considered. As a case study, you can take it forward. Now, we do have batteries. We do have vehicle transmission along with the tire systems here. Okay, you can check it out from the vehicle body. We get a vehicle feedback to the driver controller. So if I just click on this link, you see vehicle feedback going through this. It is getting to the longitudinal driver, and here the longitudinal driver takes a decision about are we going in line with drive cycle or not. So this is the drive cycle. If I double click on this drive cycle, right now we are talking about FTP 75. You have many more to work with. You have option of working with your own driving scenario. If you define it, mat file or XLS file, we can do that. Yes, we have to work with different units also. So these are all parametric level changes. You can make it at different blocks. This longitudinal driver taking feedback from the vehicle and drive cycle, it decides upon and accordingly gives acceleration command. If you check it out, the acceleration command and deceleration command is fed to the controller. Okay, so depending on that, the motor controller will command motor, and motor will fetch according to the commands received from the drive cycle from the battery. So if you look at the battery here, what do you find? You have battery pack subsystem, you have number of cells put together. Okay, if I go back into the details of cell, you can check it out. This is the equivalent battery circuit. Am I right? The modeling is a kind of behavioral modeling. Okay, is it visible? So at cell level, at pack level, we do get demand from the motor, and accordingly, motor will deliver to the transmission. So you see, this is the motor block or subsystem of the motor where we have H bridge to control this motor. So this is the motor which is been highlighted on your screen. Okay. So you see there is a kind of a mechanical part and electrical part combined together. Mechanical is highlighted by green color, whereas electrical highlighted by blue color. So there are different ways of getting into the modeling and different uh, attributes of simulation tools. Okay, so we have a mechanical rotation reference, that is casing. With respect to that, a rotor is rotating and that is fed to the gear. So whatever the motor gets the supply from battery through this controller, which is controlled based on the commands received from the acceleration and deceleration. So these are the commands received from the longitudinal driver. The controlled PWM voltage block is being used for controlling this H bridge, and accordingly a motor would work. Okay. Now we have many sensors to be utilized in between. We have many things to be look back whenever we are talking about performance analysis. So all these performance should be taken care. For example, if I go to the vehicle body, you check it out. There are many things to be taken. So this is the dynamics of the vehicle, where the rear side and front side rotation comes from the tire system. Okay, and the vehicle velocity, which could be used for many purpose, where this particular constant blocks which are used for this vehicle body, you can check it out, this W and this beta. These constant blocks are able to get us, if you would like to know what this W is and beta is, this is the resistance provided by wind. So you see the velocity in this direction, right direction, whereas the wind is in left direction. So wind provides resistance to the vehicle in the opposite direction. So that resistance can be modeled with this. Whereas right now, if I check on this block, what I am getting, the constant 10. Okay, and even I could change the unit. So wind velocity of 10 meter per second is been applied to the vehicle body, and then how the velocity of the vehicle gets. And similarly on this side, beta, this is a symbol of angle. So this gives us idea about, you see in the description of the vehicle body block, this beta gives us idea about, can you guess? Depending on the kind of picture we have. Hello? Can you guess what beta gives us? So this is the description which will help us to understand what W and beta is gives us. You can check back at this. Connections W and beta are physical signal input ports corresponding to what? Headwind speed and road inclination angle. So this W, that is the headwind speed, and this beta is road inclination angle. So this road inclination angle, you check it out, right now it is given as 0. So the simulated vehicle right now is traveling on flat path. With the unit, if I say 0 degrees or in terms of radians, okay, so I can get 0 radians that for the flat road, or I can get it a little more value to that also. So on this vehicle body parameters, if I going ahead with headwind velocity as well as inclination, what vehicle is experiencing, and then how vehicle will perform under this for different scenarios. You can check it out. There are different tires used for the front side and rear side. So these two tires will go to the NR, that is rear side. These two tires will go for the NF, so rotation to the front axle. So we do have the kind of vehicle which is been modeled as 4-wheel vehicle, 2 to the front and 2 to the rear. Now you check it out. If I go to the transmission gives us a gearbox, signal coming out from the motor, signal going to the rear axle. So the 4-wheel vehicle which we are modeling is a vehicle which is rear axle. Okay. So the input coming to the rear axle as a drive input, and you see there is a front axle on this side. What it indicates? So we have driving which is going to the rear axle, and we have brake systems which are applying brakes to the rear axle as well as front axle. So if I go to the tire block, I am getting some input to the front axle. That input is brake input, whereas to the rear axle input, that input is a combination of drive from the motor through transmission as well as there is an input from brake subsystem. Okay, so this is how we can model as per our configuration, as per our architecture of the powertrain. Now, this is all block based, right? Now, if at all I am talking about equation based, you can check it out. I do have a kind of equation based modeling here, with which I am able to calculate wheel torque or motor speed. So let us talk about motor speed. What do I have here? See, motor speed is equal to gear ratio into wheel speed. that is vehicle wheel we are talking about. So we do get wheel speed, and then we can calculate motor speed. This wheel speed, wheel torque will be also shown or seen in the scope provided. So that is the output window. So equation based, if I want to model this equation, yes, I can model it like this. So I do get signal from the vehicle speed, wheel speed, sorry, and that wheel speed, if I multiply it by gear ratio, this is the multiplication block. Okay, and then this I could get this motor speed. Okay, and then this all blocks in alteration we can make use of, provided getting it into different use. For example, motor power, battery power, motor torque. You can check it out. Wheel torque. Even there are forces which are being modeled here. F total, that is acceleration force, rolling resistance force, dynamic force, which are being modeled here. Acceleration, rolling resistance, dynamic. If you check it out, this FD dynamic or drag force, you will understand this is the equation for dynamic force. Is it visible to all of you? I hope it is in quite good resolution to be seen. Dynamic equation, which is been modeled here with these blocks. Okay. We do have a density value, then the 0.5 constant, then FA, the frontal area, then drag coefficient, all put together, multiplying it to the speed, square of the speed, and then it will give us a drag resisting force. The force, resistance force, because of aerodynamic drag. Am I right? So these all can be modeled equation based in deeper level like this. Okay. So we could get all resistance forces added together, multiplied by radius of the wheel. I will get wheel torque. Okay. So this is a kind of equation based modeling. Okay. Now you might be thinking that this equation based modeling can be utilized in this mini passenger car model. Yes, it is utilized because at the back end of the, let us say, if I talk about this transmission, okay, this is a simple gear transmission box. If I open up the parameter block for this simple gear, at the back end, of course, although we are talking about simulating, but the back end of the simulating is nothing but MATLAB, right? And MATLAB works on equations only, isn't it? So in the description, if you see, this all gives a description. At the same time, there are ways to go into the coding behind this block. For example, I could go into this vehicle body, where in the description of vehicle body block, see there is a source code. So if I click here, I will get source code for the vehicle body. Okay. So this whole vehicle body block, how or on what equations it is working, all these equations are being listed out here. Okay. If at all you want to make any changes in these equations, yes, you can do that for your particular model. Customize. You can customize your equations as per your requirement. Okay. So all these things are available as far as MATLAB is concerned. Of course, it needs that kind of subscription to the MATLAB or any other tool, as we all are aware of. It is all related with the kind of subscription we are in. Now, at our university, at our location, we do have subscription to the MATLAB, so we are able to get into back end of the different blocks. Okay, so This is how we can model. Now it has been set to the FTP 75, the drive cycle, which is used for simulating this particular mini passenger car. Now, why we are talking about mini passenger car? If you checked out incidentally while setting up this, you see mass of the vehicle is being kept to the 525 kg. Okay, do you see this block? Hello. So this is 525 kg. So particularly the weight of vehicle which is in the range of 525 kg, this goes for mini passenger car. This goes in the segment of mini passenger car. Okay. So that's why we are talking about mini passenger car subject to this FTP drive cycle, how it performs. So we'll go ahead with performance of that. Okay. I'll check upon simulation block. So this simulation, you can check it out. The stop time for the simulation is being kept as a 2474. You might be wondered why it is this golden number 2474. Those who are aware of drive cycles are aware from where it is coming. If you check it out in this FTP 75, the FTP 75 drive cycle itself is a drive cycle for that much time in seconds, 2474 seconds. So that's why the simulation is running out for the 2474 seconds. So let us have a simulation and results thereafter, so that after discussion of this modeling, I could go with the interpretation of results. That's an objective of our session, right? So I'll run this vehicle for all of you. It could take a little time. See, these are the windows popping up for results of the simulation. At the left hand bottom, you can visualize it has been in running mode, and you also can observe a kind of graph which we are getting on the window, which says the graph of vehicle velocity, and which are giving us two curves. On the right top corner, if you see red color curve is reference velocity, that is the velocity of the FTP 75 cycle, drive cycle. And in the blue color, we see vehicle velocity. Both of them are in kilometer per hour. Okay. You see, window is been simulating the results for 2474 seconds. Okay, and we are getting instantaneous velocities at every seconds. It has been building up. I hope you are able to see build of the curve on your screen. Gopal sir, if you could help me, is it visible on your screen? Building up of red curve and blue curve?
Yes, sir.
Yeah, thank you. So the red curve is the one which is defined, and accordingly, the mini passenger model which we developed, the powertrain model which we developed, is following that predefined velocity curve, but it is not able to get into those velocities, but it is delivering a kind of trend the drive cycle has, but not absolute value of the velocity. If I am interpret results correctly, the trend is being almost followed. Am I right? But absolute values are not being followed. For example, I'm talking about 500 seconds. There is a sudden drop in the velocity from almost 60 km per hour, whereas vehicle has a drop from 15 km per hour. So 16 km of the drive cycle which is expected, which is delivered by the velocity is only 15 km per hour. So you can check it out. The expectation from the velocity or expectation from the model powertrain and actual delivery from the model powertrain. I hope you are able to understand the interpreting how exactly we are going to interpret. Hello? So I was talking about, if you are able to follow, I was talking about the absolute velocities. You see, the absolute velocity, maximum absolute velocity for the FTP driving cycle is around 90, if I am not wrong. 90 km per hour. Okay, exact figure you can get it from the drive cycle data. But then the model powertrain is not giving us that maximum speed. How much it is giving? Just over 20, around 25 something. That means the model is not working properly according to the expectations. And similarly, we can check back with the other results. So if you see here, all these MATLAB windows, we have many more windows as output because that has been taken from the model. This particular window gives us about range. So you can expect after 2474 seconds, the range covered or the kilometers covered by the vehicle, it goes almost up to 40 plus, so around 45 kilometers after 2474 seconds. Are you getting it? In between, you see there is a flat line for the period which we have a vehicle standstill. Vehicle has got zero velocity. If you check it out here, see from this point to this point, almost 600 seconds, the vehicle is standstill. Velocity is 0 km per hour. So obviously, it is not meant to move from one point to other. It is stationary at one location. So there, the range curve is not increasing in that phase also. So about others, this gives you vehicle speed, this gives you wheel speed, okay, versus in the second window, wheel torque. You can compare how exactly the wheel speed and wheel torque and the timeline varies. You can have battery capacity, how it is getting up in watt hour. This is battery capacity per kilometer. So it is utilization, it is been increased, okay. Whereas we do have a kind of motor power, battery current, SOC of the battery C rate, how SOC is varying from almost 80 plus percent to the 80% during the time. So watt hour, how the consumption of the energy capacity per kilometer is. So there are different things which we can talk about. Motor speed, as like wheel speed and wheel torque, motor speed and motor torque also can be checked out. All forces can be checked out, how acceleration force is varying, how rolling resistance force is varying. You can check it out. Rolling resistance force it has been constant, isn't it? If you look back at your equation of ruling resistance, yes, it does remain constant. See the drag force, how it is varying. Tractive force, tractive power, wheel speed, wheel torque, this is what we checked out. So all these parameters can be checked out, can be interpreted with their correct understanding. Okay. Whenever the brake is applied, whenever the acceleration is there, how SOC varies, how the current, battery current varies. So I'll just check it out with the battery current, where we might have discussed a little bit. Okay. You check it out, battery current is going in negative also. What does that mean? Can anyone? Battery current going negative. What does that mean? Battery C rate. C rate is nothing but charging, discharging C rate we are talking about, right? Now, if it goes on negative side, what does that mean? Hello? If I am not wrong, all of you are aware of this. That's a kind of charging of the battery, right? The powertrain is in regeneration mode, or the powertrain is in braking mode, where regeneration, battery charging is happening. Whenever we fetch current out of battery, we say that discharging in the propulsion mode, or whenever the current is fed back to the battery, we say it negative, and we call it as a charging mode, we call it as a regeneration mode. Am I right? And that's where the SOC of the battery gets on increasing. So this is how interpretation of results can be done, and if at all we want performance to be on correct side, we are interested in first this chart. If at all your powertrain is satisfying the drive cycle scenario, then only you can check for other parameters, how they are working and all. If this is not working, then all other parameters, of course, will not be in line with what expectations. Okay. So this is what interpretation of results, and accordingly we can get. Can anyone suggest me how could I get into improvising or correcting this powertrain now? Any guesses? Any alternatives? Any ways to get this absolute velocity of the vehicle to its expected velocity? जो अभी 25 kilometer per hour, we want to make it at 90 kilometer per hour. Can anyone tell me how can we accommodate that? Or what are the reasons where vehicle or powertrain is not getting that much velocity? 90 kilometer per hour is not reaching. What are the reasons? If you are crack, what would be the reason for not getting vehicle to the 90 kilometer per hour? We are getting limit under 25. What could be the reason? If you are able to crack reasons, you are able to improvise upon the same reasons. And that's what changes need to be do in model and again test it. Okay. Hello? No suggestions? Are you all with me? charging of, okay. Yeah, that was the answer for earlier question. What could be the reason for not getting 90 kilometer per hour as the maximum velocity, or why the blue line, blue curve is not following red curve? What all reasons could be? So that's your job, right? If you model and simulate, that will not always give correct results. Rather, we can say will not give, it should not. Then only we will get to know how to improvise powertrain, how to crack out the reasons. And whenever we will be doing first time, it always is the case. Am I right? So let me close all these windows. Yes. Yeah. Anyway, you can crack upon what could be the reason why my vehicle may not be capable of doing that. Maybe vehicle's capacity is not that it goes up to 90 km per hour. Maybe a battery capacity is short enough to only give 25 kilometers per hour. Maybe control algorithm is not allowing to go beyond 25 kilometers per hour. There could be many reasons, right? There could be many things. As like one of the reason is what we said, that vehicle mass is 525 kg. Maybe this is very large enough. Maybe this is this weight for the considered powertrain is for considered battery capacity we have very large enough. So there are multiple reasons. All reasons could be tackled, and wherever as per your requirement of powertrain, you can correct all those reasons and then resimulate it and kind of expect a better results than this one. Okay, so this is what the case study. I would like to touch upon one more thing here. Check it out. At the bottom slide, we have two warnings. If I click these two warnings, it says us, because simulation at every first try, we don't get complete simulation running out easily, isn't it? We do get many errors. So here on the right hand side, you see there is a red color circle, yellow triangle, and blue circle. The red color circle gives you alert about errors in the modeling and while simulation if there are any errors. This yellow triangle is a kind of warning. You can simulate without taking care of this, but you can definitely take positively care of how this model is working out. So just check it out. Output port 1 of this model of longitudinal driver is not connected. That is what the message or warning is. Okay. And also detailing of the warning is given to convert between kilometer per hour and meter per second. So there is something mismatch about unit in the longitudinal driver. So if I go back to the model and if I check out what exactly the warning is. So do you see a single arrow here? So this is what a kind of warning we are getting for this particular model. Automatic unit conversion, kilometer to meter second, is happening here. Okay, so you can tackle that error. You can tackle that warning, second warning. You can tackle first warning because output port, this info port is open, is not connected to anything. Okay, but then without this also we can run simulation. With this conversion of unit, we may get correct results, isn't it? There are many possibilities of not getting results. Fine. So all these things can be checked it out for the running of the model, and we can make use of this model for updating with development time reduced from months to weeks, debugging time reduced almost 50% of the time, and this is a kind of very nice technology to learn to improvise or optimize electric vehicle powertrains. And in coming days, we could have more and more work in this area. Right now, I'll give you a short. I'll close this MATLAB if you allow me. So that is the end of a case study. Anyways, let it be. I'll go to the presentation slide. What we can say, we have into the case study, but taking this modeling and simulation with different tools, there is a huge requirement in the industry nowadays. Trained manpower, because as we all of us know, you also saw in the survey which I took upon initially to the start of session, there are many working professionals after post-graduation than the new entrants or students, diploma level or graduation level. Because most of the working professionals, they are in the industry, they know what industry needs. Industry is in demand of trained manpower, and they are training, they are taking, they are seeking training, they are utilizing. Even we at our university, we are helping to the Tata Motors, as well as we are being a knowledge partner to Tata Motors as well as John Deere. We are having certification programs, we are having postgraduate, undergraduate programs also. So there is a huge demand in this particular sector, modeling and simulation of EVs. Not only modeling and simulation, at all, EV domain. All of you are welcome. Recent, upcoming few years would welcome you as an EV expert, EV trained people, if you are serious enough. Okay, and if only we are serious enough, we can give answer to the question raised. Do EVs capable of leading the future? Okay, so that's where I end my talk. And if you have any queries, you can ask me on today's topic. I am open to the queries.
Participant, if you have any query, feel free to ask. Or you can post your queries in chat box also.
Sir, one question is in chat box.
Yes, go ahead.
EV domain is best for research as the number of papers are less in this domain.
Correct. So you want resources, right? Whoever is asking question, is the question complete?
Yes, sir.
Just let me check. What is the question? Can you repeat the question?
Participant has its opinion, or we can say, I think
Sir, question.
Yes, yes,
Sir,
go ahead.
domain is best for researchers as the number of papers are less in this domain.
Of course, there is an opportunity, huge opportunity in this domain, because we have less resources, everybody is working on that. So nobody is sure whether his approach or her approach is correct or not. We among ourselves need to put it in the domain. You put your work in the domain. It will be reviewed by experts, and then definitely we will get knowledge with each other, the sharing with each other. Okay.
Question from my side. Could it be a better option or better topic for PhD?
Of course, I myself is doing on the same topic. Many of our colleagues are doing on similar topics. Particularly, let me tell a brief about my topic. Just a hint. I'm working on a hybrid powertrain where I would be focusing on hybridization of batteries and capacitors together. Okay, benefits of capacitors, how we can accommodate in the hybridization. That is what my area of research. And few of our PG students are also working in similar lines, hybridization, the batteries and IC engines, even battery technology, even what different environmental conditions would electric vehicle batteries, particularly EV batteries, would face. Okay, yes, definitely. The domain is open. You can definitely check out for your PhD work, your research work.
Okay, so if anybody want to pursue his or her PhD in this particular domain, then what are the different resources or prerequisites are required?
Uh,
Is there any kind of we can say essentials are there before start of actual topic?
See, if you're talking about the students who are graduate, if you're talking about post graduation, yes, there are post graduation. Some of the universities nowadays are offering. Many of the universities are there who are offering post graduate diploma, PG level in EV domain. Very few post graduate in electric vehicle specialization are offering. We are one of them. Rather, we can say, leading. For PhD, yes, there are many universities who are working on component level, who are working on system level. Prerequisite is, see, you may be from mechanical background, you may be from automobile background, computer background, or electrical domain, electrical background. You can take upon these all uh, research areas to take forward as an application to the electric vehicles. Okay.
Okay, sir.
Yeah, someone, Gopal Patil sir, you yourself, I suppose I put a message in the chat box that software defined vehicles. Yeah, correct. So this is the need, upcoming technology. You can go through that also, how best we can make use of software data which is being created by modeling and simulation, how it will be used. A few days back, I'll just take, I forgot to mention it initially. All of us are aware, like 2 days back, we only got or experienced Chandrayaan 3 landing, right? Hello?
Yes,
All of
sir.
us
Yes.
experienced that, right? Only the thing is, what do you think before this soft landing or power landing, we call it from the ISRO? What do you think? Were there any simulations happened before this particular experiment or this particular mission? Can you guess how many simulations they must have gone through? Because earlier the landing was failed. Now we were expecting to be success. And do you think there were simulations? Of course, there were many simulations happened before this particular mission. Am I right? So you can take the advantage of simulations. Okay. Well,
If any other questions, please ask.
if there are no questions, shall I proceed? Gopal sir?
Yes, sir. Yes.
Yeah. Maybe before thanking, I would like to take your attention to this particular slide. Of course, we do offer BTech, MTech courses as well as certification courses, with which we are in connect with many research organizations and many industries in the EV domain. You may take help from us whenever you require. At the same time, at the bottom strip, there is one training, hands-on training workshop of almost 60 hours is going on. We are planning in that. We are in the planning phase. It is planned to execute in between 4th to 15th December 2023. This training workshop has been sponsored by DST SCRB, where under the Karyashala event. So this has been sponsored event. We look forward for limited seats, the EV modeling and simulation. Today we talked about modeling and simulation. In this workshop, we will be talking about EV modeling and simulation with particular tool, MATLAB and Simulink. Whatever case study we have gone through, we will get to learn in detail on this. Okay. At the same time, the similar kind of courses we do have on our university. You can take benefit of that also. What today's session we had was a glimpses of what we could do in the modeling and simulation. To take it really further, we need some hands-on training, and this is one of the training which is coming ahead. Those who want to go physically get hands-on training, they may think of this training. Okay. I'll jump to the thanking. Yes, I thank to the MIT University to provide us the platform, the student base for this upcoming domain, because as always we say this is a new age university and we are working on upcoming technologies, we are working on EV domain very exhaustively. I also thank the organizers, KJ Educational Institute from Trinity family. We could reach to you because of this FDP on this platform online. If at all the destiny provides, we will meet physically also. So I thank MIT University and also KJ Educational Institutes, and not the least, I thank all participants who have joined through Google Meeting and through YouTube. Okay, looking forward to the physical meeting, maybe in the form of the training. Okay, so thank you all of you.
Okay, thank you, sir. Before proceeding to our thanks, I want to say few important things about this FDP, being a program coordinator. So, dear participants, we have faced some issues like accessibility to participants, then internet connectivity is also there. Definitely, we'll work on it, sir. And we consider this as a learning experience because many participants unable to join for first two sessions of this FDP. But in spite of these issues, you have supported us very well, and that's why I would like to thank each and every participant for your patience, active participation, involvement, and attention as well. At the same time, I assure you that next time we will provide better platforms for such activities. But your participation and cooperation is much needed in near future also. So thank you all the participants once again. Now, I would like to request all the participants to keep their camera on so that we can take photographs of this final FDP section. So, all the participants are requested to keep their camera on. We have to take the photographs of this section. Dear participant, please keep your camera on. Okay, if possible, you can on your camera. If not, then no issue. Okay, thank you all. So at the end of this FDP, once again let me thank our speakers also who has delivered all the sessions effectively and content of all the FDP sessions very good and it was very informative sessions also. First day we have started this FDP topic overview of electric vehicle in India. And the session was effectively delivered by respected Sanjay Nibande sir. On day 2, topic battery management system delivered by Mr. Santosh Ghorpade sir. On day 3, simulation tools for implementation of power electronic systems. And this session was effectively again delivered by the Professor Harshal Wani sir. On day 4, recent advancements in lithium ion batteries. Again effectively delivered by Professor Shashank Gowde sir. And today, Professor Satish Patil sir have delivered an excellent session on modeling and simulation of EV. Uh, One of the finest experience as far as this FDP session is concerned. I hope everybody will get some idea, some research-oriented content as far as electric vehicles or future of electric vehicle is concerned. Because the topic is recent advancement and challenges in electric vehicles. So all the topics were relevant, and that's why we have planned all the topics accordingly, so that participants will get clear idea about if they want any kind of research, any kind of further studies, extension about the electric vehicles, then this FDP might be helpful for all of them. So thank you all. Thank you for your patience and active participation and your involvement also. So thank you. Now I would like to request Professor Siddharth sir to propose vote of thanks.
Before going to propose a vote of thanks, if any participant wants to be share their views, it will be great pleasure to us. Any paid participant who want to share your views, anything related to the FDP, you are welcome.
Sure, sir. We will be very happy if any participant want to say something about this FDP.
Good afternoon, sir.
Very successful only when you will have some, we can say, good opinions or we can say any good suggestions also. So please go ahead. We can give you one to talk.
So very good afternoon, sir. So I am Bhuval from Mohammed Salk Engineering College, Tamil Nadu. Today's session is very useful for upcoming graduates and the faculty and everybody. The entire session is very useful for us. So coordination, cooperation, everything fine. All speakers are very excellent. Expose their topics involvement. So thank you very much, sir.
Thank you, sir. Any other participant want to share their views, please?
Okay, fine. Siddharth sir, you can proceed.
So, respected guest of today's program, Professor Satish Patil sir, Respected Principal Dr. Suhas Khudsar, Professor Gayatri S. Patil, Head of Mechanical Engineering Department, and my dear colleague and participant. It seems to be great honor to propose a vote of thanks to all who have helped us in making this session successful. I would like to thank our today's session speaker, Professor Satish Patil sir, for making an excellent presentation and making this session very meaningful and interesting by giving real-time example simulation of real models. Sir have covered topics like MSEV, modeling and simulation of EV, timelines of advances in computer power and scientific modeling, electric motor operation modes, component modeling, system level simulation, and live case study. I would like to express our deep gratitude to KGI management for continuous support, our respected principal, Dr. Suhas Khod sir, for his continuous motivation, FDP coordinator, Professor Gopal Patil sir, and Vidyadhar Dixit sir. I am happy to express a vote of thanks to our participants who made this FDP successful through their presence and patience. Last but not the least, I thankful to all faculty of Mechanical Engineering Department who helped directly or indirectly for this FDP. Once again, thank you all for your cooperation. Thank you. Have a great day ahead. Thank you. Thank you everyone. Thank you, Satish Patil sir.
Thank you, sir.
Okay, one important announcement is there. Participants, all the participants will get FDP certificate, digital certificate after the submission of assessment test. So all are requested to submit the same, and you will get FDP certificate within a week. So it may take 7 days, 7 to 10 days, but you will definitely get the certificate. But for that, you have to submit the assessment test. Okay, thank you. A link will be shared to WhatsApp group as well as in the chat box. Thank you, sir. Thank you, Satish Patil sir. Once again, thank you.
Yes, thank you, sir. Gopal sir, I will leave.
Yes, sir. Yes, sir. Thank
Yeah,
you.
thank you.
Okay. You will get assessment link in the WhatsApp group. Yes, yes, yes. We will provide, we will share assessment link in the WhatsApp group. No issue.
Sir, what about this feedback link?
Feedback also I will share in the WhatsApp group.
Okay, sir. Thank you. Thank you.